First thing we're going to do if we're going to talk about set theory is determine what a set is. And what a set is it's a collection of objects. And the objects that are inside a set are known as elements. There are a couple of sets that that lend themselves really well to elementary school study. And just to sort of talk about those, we have one, if we use sort of a bold-faced N, that is the set of natural numbers. And the set of natural numbers are the numbers that we could count in nature, the numbers that we can count on our fingers. It's 1, 2, 3, 4, 5, 6, and that goes on forever. That's the set of natural numbers. Up next, and it's bold. It's hard for me to make a really good bold-faced W, but I'll do my best. A bold-faced W, that's whole numbers. And essentially what we do to have the set of whole numbers is we start out with natural numbers and we tack on a 0, the one that kind of looks like a hole. So 0, 1, 2, 3. What are we missing so far? What don't we have? There's a whole bunch of stuff we don't have, but what's the next thing we're probably going to add to this? What type of numbers? We don't have any decimals, Leslie, but we're not going to go there quite yet. We're going to stay simpler than that for right now. Negatives. That's the one I was after, Moylan. Leslie, you're right. We don't have decimals yet. Negatives is what we're going to add next. And for integers, we don't use I, we use Z. So that's a bold-faced Z for integers. And that is going back forever, -2, -1, 0, 1, 2, going forward forever. A way to describe integers is, and it's something we'll talk about when we get into chapter 3 later on, but it's the whole numbers and their opposites is what the integers are. Those 3 sets are sets that we will discuss periodically, so I want to make sure you're familiar with those. Decimals, Leslie, would be when we get into rational numbers, but for right now, we're just going to stick with these 3, naturals, wholes, and integers. So if I say those sets, I want to make sure you know what sets I'm talking about. Something else here that is sort of built in is when we write out all the elements of a set, there's a structure that we use. It's called roster form. What we've done is we've kind of listed out the whole roster. It's every element that's in that set. We've written it down. It's called roster form. And something that's really important that I want you to take note of is the symbol we use around the outsides of our sets. Those are braces. We do not use parentheses. We do not use brackets. So for a set, we do not use parentheses and we do not use brackets. We use braces. If you need to type braces, you'll find them on your keyboard to the right of the letter P on the, it's on the top half of that key, so you'd have to use shift to get them there. And that's how we'll type braces. We always write a set in roster form using braces. Talking about the objects in a set and another symbol for us, we can see that we have a set here because it's written in roster form. It has braces on the edges. This symbol kind of looks like an E, means is an element of. And so if we have this sentence right here, 1, that symbol, the set 1, 2, 3, what we're saying there is that 1 is an element of the set 1, 2, 3. And it's in there. That's what makes it an element. The fact that it's in there makes it an element. So it's nothing that you need to overthink. If it's in there, it's an element. One thing I want to point out, when we have braces around a collection of objects, even if it's only one object, that makes it a set. If we do not have braces, then it's an element. It's just an individual object. Putting the braces around it makes it a set. If it does not have the braces, then it's not a set. That's a really important distinction for us. Just like if we were going to say 4 is not equal to 7, we use equal to with a slash through it. We do the same thing with the element symbol. If we want to say 5 is not an element of the set 1, 2, 3, since it's not in there. 5 is not an element of the set 1, 2, 3. We use the element symbol with a slash through it. As we go through any of these terms, definitions, and symbols, please let me know if you have any questions. Real quick here, I just want you to take a minute and decide whether it's an element or not an element. So put the appropriate symbol where it would go. So essentially, we're filling in these 4 blanks right here, 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 and here. Some of these may be obvious and easy. Others, maybe not so much, and we can certainly talk about that if we need to. Make sure you ask questions if you have them. But here you're just looking for, is it an element or not an element for those 4 things? All right, so this first one here, R either is or is not an element. Well, it's in there, so R is an element of the set RSTV. And you can let me know if you have questions about any of these. 3 is not in there, so 3 is not an element of the set 1, 5, 7, 9, 19. We'll come back to this one. 4, it's in there, so 4 is an element of that set. And then finally, this one over here is a little bit tricky because it's, well, there's an R in there, but it's not a capital R. I'm not exactly sure how to answer it. I'll make sure that you do know that capital R is not an element of the set RSTV. When we work on set theory, we are going to consider capital letters as being different from lowercase letters. So capital letters and lowercase letters are different from each other. So capital R is not an element of that set. In fact, as you'll see later on, it'll be common for us to use a capital letter as a name for a set. But for right now, just make sure we understand that capital letters and lowercase letters are considered different from each other. Equivalent sets and equal sets. The definition. So this is our symbol for equivalent. It's a tilde. On your keyboard, it should be up by the number 1 in the key to the left of the number 1. That's equivalent. And when 2 sets are equivalent, they have the same number of elements. So as I look at this set here with 5 and 8 in it, that set contains 2 elements. And then I look at the set to the right of it, EK, that also has 2 elements. Since they have the same number of elements, then they are equivalent. So we would say that those 2 sets are equivalent to each other because they have the same number of elements. Equal, same symbol you're used to for equal. Equal means they have the exact same elements. They're exactly the same. 7, 12, 19, 7, 12, 19. The order that they're written in does not matter. These 2 sets are equal. They are the same as each other. The elements can be written in any order. It'll be typical for us to write them from least to greatest or in alphabetical order, but you don't have to. They don't have to be written least to greatest or alphabetical order. All right. First poll of the day, a couple of true-false questions. I want you to decide whether those statements are true or false. So the first answer choice is for the top question, and the second answer choice is for the bottom question. And so we're deciding true or false. 369 equals 693. True or false, DEFG is equivalent to DEFG. I don't think these are necessarily easy. Be careful and think about your answer. Think about what equal means, think about what equivalent means, and then make your decision. We'll go another 30 seconds and then talk about this one. Or I guess these two. All right, let's see what we've got. Okay, we are split right down the middle with a couple of outliers. It's kind of what I expected on this one, to be honest. I think the second question is a little challenging. So let's take a look here. The first one, true or false, 369 is equal to 693. Keeping in mind that equal means they have the same elements. Well, 369, 369. They have the same elements, so those two sets are equal. This one is true. And then the one down at the bottom. Okay, so true or false, DEFG is equivalent to DEFG. If you're looking at that and you're thinking, well, those two sets are equal. You're right, they are equal. But let's think about what equivalent means. Equivalent means the same number, let me do it this way, same number of elements. Well, this set over here on the left has 4 elements, and this set over here on the right has 4 elements. They have the same number of elements, so they are equivalent. That would be a true statement. They're also equal. That's true too. But as far as are they equivalent? Yes, they are, because they have the same number of elements. Let me know if that doesn't make sense. It's a really easy mistake to make because you look at it and you think, well, they're equal. So how can they be equivalent? As it turns out, anytime two sets are equal, they will also be equivalent. They have to be, because they have to have the same number of elements to be equal. The next definition we're going to look at is an important one for us, and it's the empty set. The empty set is a set that contains no elements. And that might feel a little bit strange. Well, how can you have a set with nothing in it? Well, there's just a set with nothing in it. There's 2 ways that we can write the empty set. We can either write a set of braces that have nothing in between, or you can use this symbol right here. I want to talk about that symbol a little bit. If back in your algebra history, if you had a problem like 2x equals 6, we're going to solve this. So we're going to divide both sides by 2, x equals 3. What you just found, without really saying it formally, is what you found was the solution set. You found the set of all the solutions that would make the original equation true. We are typically not that formal when we do it, but that's what we've done. We've found the set of all the answers that would make that true. If we were going to write that set, it's not the most interesting set in the world, but there it is. That's the solution set. And then you move on and you get a little further along and you get to a place where you have you haven't learned about imaginary numbers yet, and you get to a place where x is the square root of -4. And you say, okay, well, square root of 4 would be 2. But if I do 2 times 2, I get positive 4. There is no way I can solve this. This thing has no solution. And the abbreviation we use for no solution is that. It's this right here. What you're really saying when you say no solution is I found the solution set for this problem, and that set is empty. There are no solutions. This is the empty set. And so anytime you use this for no solution, really what you were saying in a much more formal way is the solution set for that problem is empty, the empty set. One thing I really want to emphasize is the empty set is different from a set that has 0 in it. A set that has 0 in it looks like this. It has an element in it. One way to think of this is like if you have a checking account and your balance is 0, or you don't even have a checking account at all. Those are very different from each other. And this set does contain an element. It's not the same as the empty set that doesn't contain any. How are we doing so far? If y'all have any questions, let me know. I know I'm going through these definitions and things pretty quickly. It's because we're eventually going to get to some problems we're going to try to solve. What is it that's confusing? Another way to think of the empty set, I think it's a really good example, is if we went to order a pizza and the toppings that they had were pepperoni, sausage, mushrooms, onions, and let's say olives, and I'll just use an L for olives. Those are all the toppings they had. And I could use any of these to create my pizza. But you know what I could also have? I just want a plain cheese pizza. Well, I can have a plain cheese pizza. As far as these toppings go, I'm not going to use any of them, but I'm still going to have a pizza. The toppings I chose was the empty set, just the cheese. And so a set with no elements in it, a pizza with no additional toppings on it, that's an example of the empty set. I hope that helps, Nicole. If not, you can let me know. We'll see more of the empty set as our day goes on. Oh, and one thing I want to say, these were strictly just to illustrate the idea that this symbol that you may have used for no solution before is technically the symbol for empty set. I'm not going to have you solving problems like this one at all. That is not part of our course. Just to make sure you know that. Subsets. When all of the elements of one set are found in another, the first set is a subset of the second. That's a whole lot of words. So I'm going to give you an example here that will hopefully clear that up a little. It's a hard thing to put into words, but it's a really easy concept to understand, I hope. The symbol we're going to use for subset is that it kind of looks like a C, but it's extended a little bit. You may also run across that symbol for subset. We're going to see these two as interchangeable. I'm going to use this one. You may run across this one in places in a book or something like that. Those two are interchangeable for us. There's no difference between subset and proper subset. We're going to treat them as identical. That's our symbol for subset. And the way we're going to use that is we can say the set AB. Oh, yeah. And notice my braces are a long way from perfect. Yours don't have to be perfect at all. AB is a subset of ABC. Now I'm going to go back and read that definition again now that we have this example here. When all the elements of one set are found in another, the first set is a subset of the second. So what we're saying here is that AB is a subset of ABC. AB is a subset of ABC. And the reason for it is because all of the elements of this set can be found in that one. It's almost like if we were all in a classroom together and I was going to split you into groups. Every group that I make would be a subset of our entire class. Our entire class is everybody. I'm going to make little subsets, and each one of those groups is going to be a subset because it came from the original. Basically, everything in here is in here. And that's what makes it a subset. We're going to look at a really good way to test whether something is a subset or not, a really simple way that I think you're going to like in just a minute. I said earlier it's going to be common for us to use capital letters as the names of sets. That's going to be true. It's basically going to save us some writing. We're going to be able to have a shorthand that we can use as we discuss different sets. Here's what I mean by that. So we're going to call this set 5, 6, 7, 8. We're going to call that set A. And then this set 6, 7, we're going to call that set B. 3, 5, 7, we're going to call that set C. So instead of having to write it out in roster form every single time, instead we can just ask a question. Is B a subset of A? And I'm not going to do a poll for these, but I'm just asking you. You can type it in there. Is B a subset of A? Good, Xochitl. Yeah, good, Moylan. Yep. And I hope you all see that, yes, it is. If I look, set B is 6, 7. Set A is 5, 6, 7, 8. Everything that's in here is in here, so yes, it's a subset. B is a subset of A. And then here's one that's going to be really valuable for us going forward. Is C a subset of A? All right, we've got universal no's. That's excellent. Very good, because it's not. You're right about that. Is C a subset of A? Is 3, 5, 7 a subset of 5, 6, 7, 8? And what's going to seem simple right now, but it's going to be a really important question for us coming up. Why not? Why is C not a subset of A? You're right. It's not. Why not? And it doesn't have to be a complicated answer. You don't have to, because of the 3. That's excellent. Perfect. Because of the 3. The 3 is a problem, right? This thing right here. This is how we're going to decide whether something is a subset or not. We're going to look and we're going to say, is there anything in here that is not in the other set? That's our test. Is there anything in here that didn't come from here? If there is, basically you can think of it like a germ that's not supposed to be there. Like, hey, how'd that thing get in there? That wrecks it. So in this particular case, it's the 3 that wrecks it. It can't be a subset because of the 3. The 3 wrecked it. Our test is going to be, is there anything that wrecks it? If there's something that wrecks it, then no, it's not a subset. If there's nothing that wrecks it, if I look up here, the 6 is okay, the 7 is okay. There's nothing that wrecks it, it's a subset. If there's nothing that wrecks it, it's a subset. Everybody good with that? Awesome. So here are 2 questions. I'm going to set up a poll for these. I do not think they're easy, but if you're patient and careful and think them through, I think you'll get them both. Maybe not. We'll see. Take your time. Think about what it means to be a subset. Think about our test for whether or not something is a subset. So these are yes or no's. Is B a subset of B? And is the empty set a subset of B? These are sort of philosophical questions as much as they're math questions. I think they're great. They set us up for the logic type of stuff that we're going to work on throughout section 1.2. Think about our test for whether or not something is a subset. Think about our test. Is there anything that wrecks it? And then you'll decide whether it's a subset or not. Abstract questions like this can be a little challenging. I promise you, we're going to get to much more concrete questions in a little bit. For right now, we're kind of still living in abstract land, and this has an important conclusion we need to get to, and I want you to spend a little time thinking about whether or not it's a subset. We'll go another 30 seconds, and then we'll talk about it. Like I said, this sets us up great for the logic we're going to work on in 1.2, the type of thinking, the analytical thought processes. Okay, we're split on this one like we were the first one. All right, that makes it interesting. Okay, good. Let's talk through this. So keeping in mind our test for a subset and what a subset is, the first one says, is B a subset of B? What this is really saying then is 6, 7 a subset of 6, 7? Well, let's see. The definition, if everything in the first set came from the other set, then it's a subset. Our test is there anything in here that prevents it from being a subset? Is there anything in here that wrecks it? Nope, there's not. There's nothing in here that prevents it from being a subset. So we're okay. So yes, it is a subset. Now your instinct might be to say, well, yeah, but doesn't it have to be smaller to be a subset? That's a reasonable instinct to have, but no, we're looking, is there anything that wrecks it? That's how we test. Is there anything that wrecks it? That's our test. Well, there's nothing that wrecks it, so it's okay. It's a subset. The one on the bottom, is the empty set a subset of B? Is the empty set a subset of B? Oh, wait. Empty set doesn't have a 0 in it. Is the empty set a subset of B? Here again, is there anything that wrecks it? Is there anything in here that would prevent it from being a subset of B? And I'll give you a second on that, because this whole idea of the empty set as an abstract idea can be a little bit difficult. But remember our test. Our test is there anything that wrecks it? And Leslie, you're right. No, there's not. There's nothing in here that prevents it from being a subset. That's our test. There's nothing that prevents it. I can't say it's not a subset and here's why. There's nothing that prevents it from being a subset. So is the empty set a subset of B? Yes, it is. The conclusion that these two things point us towards are two different rules related to subsets. The first is that every set is a subset of itself. B is a subset of B. There's nothing that's going to wreck it. So every set is a subset of itself. And then the other one down here, this one leads us to the conclusion that the empty set is a subset of every set. No matter what our set is, the empty set is going to be a subset of it, because the empty set is never going to have anything that prevents it from being a subset. Instinctively, these both feel a little strange, but if you remember what our test is there anything in there that wrecks it? Hopefully you get to a place where both of these are comfortable and make sense. Fine, that's the rules, then that's the rules. There's nothing in here that wrecks it, so every set's going to be a subset of itself. There's nothing in here that's ever going to wreck it, so the empty set is going to be a subset no matter what set I'm given. Are questions or discussion about that before we do a little bit more with subsets? All right. Finding subsets. So I'm given those same three sets, and my job here is to find all the subsets of B. And if you're thinking, all of them, gosh, how many will there be? That's a good question. We'll get to that in a minute. But if I want all the subsets of this set right here, what I want to do is I'm going to start out with the biggest number of elements I have. This set has 2 elements in it. So I'm going to need the subset with 2 elements. Then I'm going to look for all the subsets that have 1 element. Well, let's see. That would be this one and this one. Do I have them all? Do I have all the subsets of B? We're split a little bit. Jessica, Emily, what am I missing? Then Nicole, if you think of it, outstanding. I'm missing the empty set. So there it is. So what I did was, this set has 2 elements, so the biggest subset's going to have 2 elements. Then I need to write down all the subsets that have 1 element, and then I don't want to forget about the subset that has no elements. And I wind up with 1, 2, 3, 4 total subsets. I'm going to have you try one. How many subsets of C are there? I'm going to set up a poll for this, and when we answer the question, we're going to write out all the subsets. As far as the poll goes, I'm just going to ask you how many there are. And so here we're after the total number of subsets. How many subsets are there? Something that will happen with some of these set theory questions in the very beginning is, they just don't feel that intuitive. But after you practice and after you've done some and you kind of figure out, oh, that's how this works, then you get it. Like the idea that, that equivalent sets are sometimes equal also. Equal sets are always equivalent. Oh yeah, that makes sense. Those kinds of realizations come to you the more you work with it. We'll go another, 20 seconds on this one. Let's see what we've got. Split again. Interesting. Okay. Definitely interesting polling today. That's for sure. Kind of fun in a way. It's great when we're unanimous and we're all correct. For these, it makes for interesting discussion because I think once we talk about it, you're like, oh, yeah, that's what I did. It's not usually a concept that's so complex that the explanation doesn't clear it up. So we need subsets of C. And C has 3 elements in it. So the biggest possible subset has 3 elements. and that's going to be the set 3, 5, 7. We know we have to count that because every set is a subset of itself. Then we need the subsets with 2 elements. So that'll be, let's see, that's 3 with 5, 3 with 7, and 5 with 7. Then I need the subsets with 1 element. That's the 3, the 5, and the 7. And then we don't want to forget about the subset with no elements, which is the empty set. And so when all is said and done here, it looks like we have 1, 2, 3, 4, 5, 6, 7, 8 subsets. So how many subsets of C are there? There are 8. One thing I'll tell you is we just did a couple of these. When we looked at B, it had 2 elements and it had 4 subsets. We just looked at set C that had 3 elements and it had 8 subsets. If you're thinking, if we had to find the subsets of A, that's going to take me forever to list those out. You're kind of right. You could do it, but it would take a little while. I'll tell you there is a shortcut, but it's a pattern recognition shortcut. That's one of the homework problems. So I don't want to totally give it away, but this is your starting point. I'll give you that much. So there is a shortcut, and I think you'll find it. If not, we can certainly talk about it at a later time, but I think you'll get it. All right. There are operations we're going to do with different sets. The first operation we're going to look at is called intersection. And just like if we had 2 roads that come together, they have an intersection. When those 2 roads come together, there is an intersection of those 2 roads. And the intersection of 2 sets is the overlap. It's what they have in common. It's the part of the road that's in both sets. Our symbol for intersection, our abbreviation, is going to be that. Really easy to remember because it's kind of in the word intersection. And so when we're looking for the intersection of 2 sets, what we're looking for is the overlap of those 2 sets, the elements that they have in common, the elements that are in both sets, the elements that are in the first set and in the second set. And's a really important word for us that goes with intersection. So for example, if we wanted to find A intersect C, what we're looking for is, where's the overlap? What elements do they have in common? And so that's going to be a set where A and C overlap. What elements do they have in common? Well, they both have the 5, and they both have the 7. So the intersection, A intersect C, would be 5, 7. It's where they overlap. It's what they have in common, the elements that are in both sets. It'll probably take me longer to type this than it will for you to do it. I'm going to set up a poll for you to find B intersect C. The terms and definitions are mostly behind us. Now we're getting to the part where we get to do some more concrete problem solving type stuff that I think you'll like. So find B intersect C. Notice what we're after is a set, and so we need to use braces when we write it, and it's in roster form. We're looking for B intersect C. We'll go another 20 seconds and then talk about it. Let's see where we are. Okay, unanimous. Now we're back on track. Very good. Outstanding. So when I want B intersect C, what I'm looking for here is the elements that are in B and in C. And the only thing is the 7. So B intersect C just has one element in it. It's a 7. Excellent work. Very good. Okay. Another operation we're going to do is called union. Our abbreviation for union, our symbol for union is just the same symbol as it was for intersection, turned upside down, kind of looks like a capital U. And it's easy to remember since it's the beginning of the word union. Oh, one thing I should mention, you may have noticed it in the poll, you may not have. We can type a capital letter U to represent union. We can't really type that symbol to represent intersection. So when we're typing it, if you're typing an email to me or I'm typing an email to you or in the poll, I'm going to use that symbol. It's Shift 6 to represent intersection. It's the caret. Same thing we use for an exponent, but clearly here we're not using it for an exponent. Okay, union, more instead of an intersection of two roads, we can still think of the two roads. I like that example, but instead of the intersection and where they overlap, with a union, you can think of it more like a wedding. We are taking this road and we are joining it with this road. We're counting all of it. We are joining them together. So as far as union goes, we are joining them together. We are looking at the elements that are in one set or in the other set. There's an important thing about the word or that I need to mention here. When you go to a restaurant and they say, do you want soup or salad? You don't get to say yes, meaning I would like both. When they say soup or salad, they're using exclusive or. You get one or the other, not both. That is not the type of or we use in set theory. We use inclusive or. And what that means is when we say or, it's if you're in the first set, we keep you. If you're in the second set, we keep you. If you happen to be in both sets, we keep you too. This is inclusive or. Anything that's in one set or the other, we keep it. And so the way that we're looking for elements here is anything that is in at least one of the two sets is good enough. Here's an example. Let's say we wanted to find A union C. What I'm going to do is I'm going to take A and C and join them together. I'm going to take A and C and join them together. While I could write down A and then write down C right after it, and there's nothing wrong with that, I'm going to put them from least to greatest just because that's kind of our convention. So let's see, I have 3, 5. Do I write the 5 twice? That's a really good question. No, we only write it once. Once it's in there, it's in there. So we don't need to write it twice. So we have 3, 5, 6, 7, 8. I think that's it. 3, 5, 6, 7, 8. I join those two sets together to make a new one that is A union C. Similar to last time, now I want you to find B union C. I'll put a poll for that. We want B union C. We want to join them together. We're going to keep anything that's in B or in C. If it's in at least one of those two sets, we keep it. We'll go another 20 seconds, and then we'll do this one. Let's see where we are. Almost unanimous, not quite. Let's go ahead and take a look at how we got there. So for B union C, what we're doing is we're joining those two sets together. So we're taking anything in B, joining it with anything in C. So we're going to have 3, 5, 6, and 7. We don't need to write the 7 twice. It's 3, 5, 6, 7 because we joined them together. Take everything in B, join it with everything in C. There's B union C. Any questions about intersection and union? Before we move on to, really, we just have 2 more ideas in this section. We're going to do a lot of practice, but this next idea is a big one. So I want to make sure we're comfortable with intersection and union before we go forward. Based on the polling, I think we are. Universal set and complement. If there's anything that's going to give you trouble in this section, well, at least what we're covering today, it's the complement. First, the universal set. The universal set is all the elements under consideration. We're going to use a capital U for that. Technically, it should have a tail, or it should have a tail on it, so it doesn't look like the symbol for union. It's obvious it's not the symbol for union because it would give us a set afterwards. So that's how we know that's the universal set and not the union. So what we've got there is, here is my universal set. That's my universe. That's all the elements that could possibly be considered for this particular problem. Then we get to the idea of the complement. The complement of a set are all of the elements that are outside of the set, but inside the universal set. Let's see, outside the set, but inside the universal set. We better look at an example and then go back and revisit that definition. So if I were to say, what is a complement? Oh, and our symbol for complement. There are a couple different symbols used for complement. One of them is to put a bar over the top. That's really hard for us to type. So we're going to use the apostrophe. Those are both acceptable ways to write the complement. I believe our book might use the bar over the top. We're going to use the apostrophe because we can type it. So if we want to type complement, we're going to use the apostrophe. So a complement looks like this. And a complement is all of the elements that are outside of the set, but inside the universal set. So it's everything else. So everything in this whole universe is right here in this set. And set A is made up of 5, 6, 7, and 8. So the complement of A is everything else. So A was 5, 6, 7, and 8. So a complement is everything else. That's the 3, the 4, and the 9. So a complement here is 3, 4, 9. It's everything that's outside the set, but inside the universal set. So everything else that's not in set A. Complement can be challenging, so I don't mind if you have questions and we have to be patient about this. I want you to take a second and try to find B complement. I won't set up a poll, but take a minute, try to find B complement, and then we'll talk about it together in just a minute. So B complement is everything outside of B, but inside the universal set. I'm hoping what you came up with for B complement is you said, well, B is 6 and 7. So that's 6 and 7. So B complement is everything else. 3, 4, 5, 8, 9. If B complement as 3, 4, 5, 8, 9 makes sense? Fantastic. That's great. Understanding what the complement is the biggest hurdle in what we talk about all day today. If that makes sense, we're on a good path going forward. If not, please let me know. All right, let's do some more practice. Basically, from now till the end, we're doing practice, except for one more really easy idea that's last. But so intersection, union, and complement. We've got all right here on this page. You can see them down here. We have intersection, we have union, and we have complement. They're all on this page. Intersection, union, and complement. Those are my sets. The universal set, 0, 2, 4, 6, 8, 10. A is 2, 4, 6, 8. B is 6, 8, 10. And C is 2, 6, 8. I'm not going to do a poll here, but I am going to just sort of give you a chance to do these and see how they go. And then we'll talk about them together. The first one, A intersect B. I'm guessing you probably didn't have much trouble thinking about that one. It's intersect is overlap. I want the elements that are in both sets, the elements that are in A and in B. And as I look at sets A and B up here, what I can see, the things that are in both looks like the 6 and the 8. So A intersect B is the set 6, 8. If that doesn't make sense, if you're not sure where it came from, please don't hesitate to ask. Down at the bottom, we want A union, B complement. A reasonable question here is, well, do I find A union B and take the complement of that? Or do I find B complement first and then do the union thing? Great question. Excellent question, if that's what you're thinking. In this particular case, we do the complement first. If you were supposed to find A union B first and then take the complement, it would be written using parentheses. So parentheses are going to be used the same way in set theory as they are in order of operations. If there are parentheses, we do that thing first. If there are not parentheses, like we see here, then we find what A is, we've already got it, find what B complement is, and then join those two sets together. So the first thing we've got to do to answer this question is find out what B complement is. Remember, B complement is everything outside of B, but inside the universal set. So let's see, B is 6, 8, 10. So B complement is 0, 2, 4. If anything that I'm writing down or saying isn't clear, isn't making sense, you're not sure where it came from, just ask. I'm sure you're not the only one with the question. Then, once I've got B complement, now I've got to find A union B complement. Remember, union means join together. It means the elements that are in A or B. If you're in at least one of the two sets, we're going to keep you. Oh, well, we got a lot more practice to do, Courtney, so I think it'll probably come home, but I can talk about B complement over here for a minute. B complement is everything that is outside of B, but inside the universal set. And so if B is 6, 8, 10, that's these. B complement is everything else, the 0, 2, 4. No, not at all. Go ahead.
Okay, I'm sorry. Okay, so for the union, like that's the base for all what to expect for A, B, and C. Is that the first one?
No, this up here isn't union. That's the universal set.
Universal
That
set.
is the universal set, which is the set of all the elements that are under consideration. The symbol looks like the symbol for union, but we know it's not union because it's telling us U is equal to this over here. And so it's a set. And so it's the universal set.
Okay, so
Technically, that U should have a tail on it, but we can't really type it that way.
Sure.
Go ahead, I'm sorry.
So whatever isn't, so the B complement is whatever isn't in whatever isn't in B but is in U.
Yes, perfect.
Okay.
That's you've got it. And that's the idea of the complement is everything that's outside of B but inside the universe. When we looked at those sets at the very beginning, when we were looking at those sets in the very first problems we were looking at, we just had sets A, B, and C. We didn't have a universal set yet. We didn't need one. But when we get to complement, we need a universal set, because now we have to say, here's everything under consideration. That's it. Those are the only numbers that exist in the whole world for this particular problem. If B is this, then B complement is everything else. And when we say everything else, we mean with this restriction in mind. So it's not all the other numbers besides 6, 8, and 10. It's all the other numbers besides 6, 8, and 10 that are in here. And that's how we find B complement.
Got it. Thank you so much.
Yeah, no problem. So now we want the union of A with B complement. We want to join those two sets together. So I look and I see that A is 2, 4, 6, 8. B complement is 0, 2, 4. And when I join those, then I'm going to have 0, 2, 4, 6, 8. They don't have to be written from least to greatest, but it's kind of, it's think of it as good grammar, if you will. Because if you put A is 2, 4, 6, 8, and the only thing I need to add on because of B complement is that 0 and put it at the end, it's not wrong. It's perfectly fine. It's just that sort of the way we're going to do them to finish it off is least to greatest. Questions about those before I have you try some? All right. Same sets as we had before. We have our universal set, then we have A, B, and C. And what you're after is C complement union B. There are no parentheses here, so we're going to find C complement, we're going to find B, and we're going to join those together because it's union. It's probably more information than I should give you. I'll give you less hints on the next one. We have a few of these we're going to do. We're after C complement union B. I'll type this up, and you can find the correct set. Okay, we'll go another, 15 seconds and then talk about this one. Okay, we're not unanimous, but we do have strong agreement here. So that's pretty good. All right, let's take a look at this. If you see anything that doesn't make sense, make sure you ask about it. So for this one, what we're going to have here is we're going to start out by needing C complement. So the first thing we've got to do is find C complement. So I'll go over here and I'll put C complement is. C complement is going to be everything that's outside of C but inside the universal set. My universal set, that's all the numbers that exist for this particular problem. And C is right here, 2, 6, 8. So C complement is going to be everything else. If C is 2, 6, and 8, then C complement is going to be 0, 4, and 10. First question, if anybody doesn't know where C complement came from, it's okay to ask. Now once I have C complement, I want to join that with set B. So C complement over here, joined with B over here, looks like 0, 4, 6, 8, 10. And so there's C complement union B, 0, 4, 6, 8, 10. I kind of think these problems are like puzzles and they're really fun. And typically, once we get the hang of complement, they don't have to be that challenging. Intersection and union, we did great with those. Now we just have to fold the complement in. These will gradually get more difficult though, I promise. So let's take a look at this one. Here we have A union C complement. I'm going to do a poll for this one too. The parentheses mean something. Just like in order of operations, we do what's in the parentheses first, and then what's outside the parentheses comes after. So here we're after A union C complement. So the parentheses tell us what to do first, just as a reminder. That means find A union C first. And then after that's done, we take the complement. We'll go another 20 seconds and then talk this one through. See where we are on this one. Strong agreement, but not unanimous. That seems to be where we've been on the last couple. I hope we're clarifying any questions you might have. If you didn't get it correct, I hope what we're doing is making it make sense. If it's not, please ask. This is the perfect time to ask questions. So we need A union C complement. So the first thing we need to do here is find A union C. Remember, union means join together. Anything that's in A, we keep it. Anything that's in C, we keep it. A is 2, 4, 6, 8. C is 2, 6, 8. So when we join those together, we get 2, 4, 6, 8. Really, joining those together just gave us A. It's just a coincidence how it worked out, right? A and C just happen to overlap quite a bit. There's A union C. Now what I want is A union C complement. So I need the complement of that set. Everything that is outside of here, but inside the universal set. One thing I will give you a little bit of a heads up on, make sure you're looking to see if there's little apostrophes when you take a quiz, especially. There could be an apostrophe there and you don't want to miss it. Just make sure you look. Okay, so if A union C is 2, 4, 6, 8, then everything else that's in the universal set is 0, 10. And so A union C complement is the set 0, 10. I've got one more poll for you, and then a couple more problems I want to talk about. One more poll. This one really ramps it up. We've kind of hit the top of the mountain on this one, just to sort of get you pointed in the right direction. We have parentheses, so we start there. We're going to do B union C. We're going to take the complement of that, and then that's going to intersect set A is the last thing we're going to do. So first, B union C. Next, take the complement, and last, intersect with set A. So that's our steps here. The parentheses go first, just like order of operations. The apostrophe, which does our complement, goes next. And then the last thing is over there on the left, the intersect with set A. And this is about as complicated as these can get. You know, if you look at this one problem has intersection, union, complement, and parentheses. This is as complicated as they get. If you feel confident and comfortable with this one, then you're in really good shape for anything that this part of section 1.2 is going to throw at you. If not, this is something that definitely gets easier with practice. Nicole, always is a big word, so I want to make sure I understand what you mean. Because we have parentheses, that's where we start. If we didn't have parentheses, we just go left to right. But if we have parentheses, we start with the parentheses for sure. And you'll just have to be flexible with what you're given. But if there are no parentheses, you'd go left to right. I'll talk about that in just a second. We'll finish this one up in another 15 seconds. See where we are here. Again, not unanimous, but strong agreement. That's a good, solid place for us to be. I think that's okay for us. So In this one, what we're going to do first, because the parentheses are there, the parentheses tell me to do B union C first. So I'm going to start by finding B union C. And that's going to be, let's see, I need B joined with C. Excuse me, that'll be 2, 6, 8, 10. Now the next thing I need to do is take the complement of that. So I want the complement of that set. So B union C complement will be everything that's outside of here but inside the universal set. Well, let's see. That was 2, 6, 8, 10. So B union C complement is 0, 4. If you see anything that you're not sure where it came from, please don't hesitate to ask. Now I have 0, 4, and what I want to do with that is, now this thing, where I am now, I want to intersect with set A. So I want to know, where does this set right here intersect set A? What do they have in common? And the only thing they have in common is the 4. And so A intersect B union C complement is just a set with the 4 in it. That's it. One thing that Nicole mentioned about the parentheses, if this was A intersect B union C complement with no parentheses at all, we would just do this left to right. We would start by doing A intersect B. We would find C complement, and then we would find A intersect B, find C complement, and then join those two things together. One that I'm not going to set up a poll for, I'm just going to do for you real quickly. Now I've added a set D in here. Same sets as before, I've just added a set D, and it says A intersect D. And so I want to know, where does set D intersect set A? They don't. What's my answer if they don't intersect at all? Outstanding, Courtney. Very good. And I hope everybody that's typing is right. Perfect, Leslie. That's a great way to type it. You could type this way. I don't know if you could type it this way, but that would be a correct answer. Or you could just say empty set. That'd be fine with me. Please be aware that the empty set can be an answer sometimes. If there's no overlap between the sets, then the answer is just the empty set, and that's okay. One last concept for today, and that concept is cardinality. Cardinality is sometimes so easy that students make mistakes with it. What the cardinality of a set is the number of elements that a set has. That's what the cardinality is. How many elements are in it? I can tell you, I like asking cardinality questions on quizzes and exams because you don't have to type roster form. Instead, you just tell me how many elements are in it. And so an example of that might be, oh, and the way we denote cardinality is with this little lowercase n in front of the set. So that lowercase n means cardinality. If you want to think of it this way, what it's asking you is, what is the number of elements in the set A intersect B? That's what's going on there. That's what that lowercase n means. It means we're after the cardinality, which is the number of elements in the set. So the number of elements in A intersect B, first I'll have to find A intersect B, and that's, let's see, looks like 6, 7. And so the cardinality of that set, the number of elements in that set is just 2. We don't use braces, it's just a number. Our answer is just 2. The number of elements in C complement. First I've got to find out what C complement is. 3, 5, 7, so 3, 5, 7. So C complement's going to be 4, 6, 8, 9. And then if I'm asked for the cardinality of C complement, I don't type this. I don't list out the set. Instead, the cardinality of set C complement is what? What's the cardinality of C complement? Perfect, Nicole, Emily, Moylan, Michaela, excellent. It's just 4, because that's how many elements are in that set. And that's it.